Hi everyone, welcome to the Big Data Analytics tutorial series organized by the IEEE PES Big Data and Analytics for Power Systems Subcommittee. This is Qiu Shi from Arizona State University. Today we are honored to have Professor Ali Abur from Northeastern University. The topic of today is tracking faults and network model changes using Phasor measurements. As we all know that an increasing number of PMUs are installed on substations and transmission lines, providing valuable data and at a very fast speed. In this tutorial, Professor Abur will first describe a fault location procedure based on a limited number of PMUs to detect and locate fault on any of the transmission lines. The same approach will be also used for detecting unreported topology changes. Finally, Professor Abur will present a tracking estimator for non-transposed three-phase transmission line, which will enhance the performance of protection and control. So this tutorial will be around 90 minutes long. At the end, there will be a Q&A section. If you have any questions, you can send your questions to me through the chat box. And as usual, I will give the speaker to Professor Wang, who will have an introduction of Professor Abur.
All right, thank you, Qiu Shi. It's my honor to have Professor Ali Abur here. He received his bachelor in Orta Technical University from Turkey, and he got his master and Ph.D. degrees from Ohio State University. Then he joined the Department of Electrical Engineering at Texas A&M, where he worked as a professor between 1985 to 2005. In 2005, he moved to the Department of Electrical Computer Engineering at Northeastern Universities in Boston and served as the department chair until 2013. He's currently a professor in the same department. He's a fellow of IEEE. Just before we start, I want to highlight his contribution in the domain of state estimation. I have been learning all of his materials all the time. Actually, 2 days ago, Professor Vijay Vital was talking to a comprehensive exam student and mentioned Professor Ali Abur's work and how it impacts to stability. Without further delay, Professor Ali Abur, thanks, and please have your talk.
Okay, thank you very much for the generous introduction. And I suppose you can hear me well, right? My voice is coming through. Okay, thank you.
Yes.
Yeah, thanks. It's really a big honor, privilege to be here, talking to this very distinguished group of people, colleagues. Good morning to people from the West Coast, and good afternoon, everyone, and also good evening to our friends in the eastern part of the world. So one good thing about having these virtual meetings is a lot of people can contribute and also attend. So that's really an added advantage. So I'm really glad to be here, and thanks also for the invitation coming from this tutorial series committee. So what I'd like to do today is to give an overview of a topic which is interesting, because I will actually be talking about one approach, but multiple applications, which doesn't happen too often. But when it happens, I think it's a clear indication that maybe there is more room for research and advancement. So hopefully this will motivate other work by everyone. So before I start, typically what happens is you give a talk and it takes too long, and at the end you completely forget about the acknowledgements. So I decided to do the acknowledgements at the beginning. There are two types of acknowledgements here. One is the money, the funding that helped us to do the work. So of course we are indebted to National Science Foundation and the Department of Energy. And both of them also, through them, having established this engineering research center with other colleagues from other universities, the CURENT. I'm indicating it on purpose because it's not a typo. It's not current, but CURENT. And if you haven't been following this ERC's work, a very small part of it is ours, but it's a very large center. So I'm sort of giving a push here for current. And then, of course, not last but not least, the students who contributed to this, who are now themselves Ph.D.s and working researchers, starting with Guang Yu. Fang, she contributed a lot to the fault location problem, derivations, formulations, and then followed by Arthur Moko's work, who also did a lot of improvements on the fault location problem. And then Bilgehan, who recently graduated with a PhD, his contributions are in the area of external network modeling error detection, which I'm going to review briefly. And then Pangshang Ren, who got his PhD a couple of years ago, he did a lot of work on parameter error tracking, which I'm going to also talk about towards the end of the presentation. And of course, I'd like to mention the help and assistance, and of course, the friendship of my colleague, Professor Anok Levari, who recently retired, but still very, very active and very distinguished colleague of mine. So after this, I'd like to move on to the outline of my talk here, tutorial. As in the introduction, they mentioned that I'd like to go over briefly Phasor measurements, even though I'm sure everybody knows by now what they are. And then I'll talk a bit about the so-called sparse estimation problems. And then we'll go over two applications of that. One is fault location, the other is the line outage identification. These are age-old problems, as you know, nothing new in terms of the topics, but we will see some new edges, new approaches to these. And then finally, I'll turn my attention to line parameter tracking problem of transmission lines. All of these approaches obviously use Phasor measurements, and that's sort of the common theme of the talk. And then close it with some remarks. This is a tutorial, but not necessarily a literature review. So I'm not really pretending that I'm going to cover everything about these topics. In fact, I cannot. But as you know, it's a very, very richly covered topic. The literature is very, very rich, both in the area of fault location and also in the area of detection of lines, line outages, and so forth. So in advance, I apologize for all the missing long list of literature. I'm going to be talking about a very, very narrow application here related to what we have done so far on these topics. So you have seen this picture before, I'm sure. In North America, this is showing the locations of the PMU installations. And this is pretty dated, actually almost 7 years old. So I'm sure the picture is quite different now, but it shows you the hierarchical structure of the PMUs. The blue dots represent the PMU locations. And then there are yellow stars, which represent the local PDCs, the Phasor data concentrators. And then these PDCs report to the so-called regional data concentrators, and those are indicated by red stars. And the arrows, red arrows, indicate the information flow or the data flow. So the PMUs report to the local PDCs, the local PDCs report to the regional PDCs, and then there the data is collected and then redistributed, used, and so forth. Now, if you look at more closely to the device, actually, this is a very simple but sort of clear representation provided by, as I'm indicating at bottom here, Power System Relaying Committee Working Group. And you see that given a PMU, you are actually collecting two types of data. One is the voltage, the other is the current. These are coming from the instrument transformers, CTs and PTs. And the actual sampling is pretty high, perhaps maybe 48 times a cycle. But then these samples are time-stamped using a GPS clock. So with these time-stamped samples, you develop or you calculate and recover the equivalent phasor. And then you send that phasor to the local phasor data concentrator. And of course, this data concentrator also receives data from other PMUs, as shown here. And since these are all time-stamped data, PDCs can align them in time and then that way provide a nice synchronized set of measurements to whoever. It could go into a corporate PDC, it could go to a regional PDC, could be used as a backup, it could be used in offline or online applications. So in a nutshell, this is the hierarchy, this is the sort of the architecture we are looking at. Now, if you consider the PMUs themselves, at a given substation, typically we measure not only these PMUs measure not only the voltages, but also the currents on these lines incident to that substation. And even though the measurements are indeed three-phase, the reporting is typically done in the positive sequence. So when you measure these phase voltages, you go through this classical symmetrical component transformation, and then you pull out the positive sequence component, and that's what is reported by the typical PMU. So PMU will report the positive sequence voltage, positive sequence currents on these incident branches that it's monitoring. We will also assume that we have access to individual phase phasors, phase voltage and phase current phasors in certain applications, but I'm going to highlight them when we cover these. Okay, now I'm going to come back to this problem, so-called sparse estimation problem. Actually, it's nothing but an underdetermined set of equations, as you can see here, which is written in sort of compact matrix form. You have a large number of unknowns, which are put into this vector beta. And in this vector, we have P entries, so we have P unknowns. But I only have N equations, where N is much smaller than P. So, I mean, you can think about applications where you have only maybe 4 or 5 equations, but maybe 100,000 or 1 million unknowns. And obviously, if you write these equations, it's hopeless to expect to get a solution because it's completely underdetermined. So these problems typically don't have a solution, but there are certain problems, certain applications where these equations will have an additional feature, an additional information buried in the problem statement. And that would be, for instance, if you already knew that beta, this unknown vector, is extremely sparse. How sparse? Well, for instance, we have this term called k-sparse. If a vector beta is k-sparse, that means that k out of p entries in this vector are significantly larger compared to the remaining p minus k entries. The problem is, even though we know this, what we don't know is which of these k entries out of p are like that. So we know that it's extremely sparse. There are only k significant entries, but we don't know which k are those. And then we can resort to these techniques, which are referred as the sparse estimation techniques. So if you have a set of equations like this, and you know that they are underdetermined, but in addition, if you know that beta is a very, very sparse vector, this unknown vector, then you can attempt to solve this problem by the so-called sparse estimation methods. What are those methods? Well, these methods were initially suggested by Tibshirani with this famous paper in 1996. And Tibshirani essentially showed that typically when you are solving this sort of equation, where you are trying to minimize the sum of squares of the residual, sum of squares of these differences between the measured values and the so-called estimated values, you can add a term here, and together with that, you can try to minimize the sum of absolute values of the unknowns. And you do it through some tuning parameter lambda, which is positive, and it changes during the iterative solution. And he called this his approach least absolute shrinkage and selection operator, or LASSO. So this is typically referred as the LASSO solution. And then, of course, this was very powerful, and it had many, many applications in engineering and other sciences and so forth. So as a result, we have seen a large variation of this in the literature since '96. There have been many, many papers, many different variations of this implementation of this solution. And then I would like, I couldn't pass without mentioning one name here, and that's George Dantzig. And in fact, in 2007, there was a paper from Caltech and UCLA, and there they referred to their implementation as the Dantzig selector. And rightfully so, and it's sort of homage to Dantzig, who unfortunately passed away about very few years, like a couple of years before this paper was published, because as you probably already know, Dantzig is the father of linear programming, or I should say the father of the simplex algorithm, which is the way you solve linear programming problems. And in fact, in this paper, they showed how this problem can be put into this linear programming formulation and solved. And therefore, the fact that we are actually solving this, also the majority of the credit goes to George Dantzig. And if you are, of course, in the area, you are working in the area of optimization, you are very well, very familiar with George Dantzig's work, but if you haven't done any work, I would definitely recommend reading Dantzig's works, papers and books and so forth. So now, why are we talking about these sparse estimation problems? Because if you look at engineering and economics and business and so forth, you see a lot of examples where problems can be formulated as the sparse estimation problem. And in fact, in power systems, we noticed that there are at least two problems which we work on, which can be also presented, which can be formulated in this form, and therefore take advantage of this very powerful method of solving these systems of equations. If you look at the statements of these problems, the first one being the fault location problem, If you state the problem, well, large number of candidate branches, you are given a big system, and there are lines and transforms and so forth. So along one of these branches, there is some fault. So among these large number of candidate branches, one of them is the faulted branch, and the question is which one? Now, there's a further complication in the case of the fault location problem. That is, on that unknown branch, we also don't know where the fault is. So unknown fault location along that suspect branch is an additional complication. But the basic problem of identifying the faulted branch is similar to if you are looking at a problem of identifying a line outage in a given system, particularly in a setting where you have an internal system with a well-measured, well-monitored system, but then you have an external network which is not that well measured. Perhaps you have some missing links, missing data coming in. So in that case, you're interested in determining what's going on in the external system. Maybe there's a major line outage and you wish to detect it. And that problem also, when you state it, it sounds very much like this problem. You have a large number of candidate lines in the external system, one of which is disconnected. Which one? So as you can see, even the straight verbal description of the problem sounds similar. Indeed, when we formulate these problems, we can show that they can be formulated exactly the same way. So this is sort of what I'd like to present here. So let's start with the fault location. So you can picture it very simply like this. You have a system, you have a bunch of lines and substations connecting them. And one of these lines is faulted. We don't know which one. And there are very few places where we can install PMUs. Unfortunately, we don't have the money and the means to install PMUs at every substation, but maybe in a given system of, I don't know, 10,000 buses, maybe we have 50 or 60 PMUs. And then based on these PMUs, can we actually determine the fault location when there's a fault along any one of these lines in the system? So this is the problem. If you look at the other problem, the external network problem, it's sort of similar. You have a system. Part of this system is what we call the internal system. So this system is our system. It's a fully well-monitored system. We have enough SCADA to run our state estimations. So at any point in time, or at least every few minutes, I can update my voltages, currents, angles, everything. And however, the external system is not as well monitored. In fact, it may not be monitored at all. I may not be receiving any real-time measurements. And however, I'm interested in what's happening in the external system, especially if there's a major line outage. And the reason is because I need to run my real-time contingency analysis for my internal system. And my real-time contingency analysis is very much a function of what's happening in the external system. So this is very important information for me. And I would like to determine that, if possible, without requiring extensive monitoring of the external system, relying mainly on the measurements I have on my internal system and at the boundary buses. So this is the line outage problem. So coming back to the fault location problem, as I said, there are two things that we would like to discover or recover. One is which branch is faulted. So I'm interested in finding out the branch number. And then I'm also interested in, once I know that, I'm interested in figuring out this distance from either end of either terminal of the line, faulted line, so that I know exactly where the fault is. So therefore, I'm interested in figuring out this distance x. Okay, so let's look at the fault location problem. The history is long, the literature is rich. So many people brought contributions and solutions to this problem that it's difficult to cover everything. But you can sort of group the solutions into three major categories. One category is solutions relying on power frequency methods or impedance-based methods. where you filter out the high frequency signals from the fault signals, and then you estimate the apparent impedance to the fault from one end of the line and variations to it. Now, in the second one, we have traveling wave-based methods, and these methods typically try to do exactly the opposite, remove the power frequency and then concentrate on the high frequency and capture the traveling waves and then use the time of arrivals and so forth. And based on that, determine the location of the fault. And then finally, there's a third group where people use artificial intelligence, pattern recognition, machine learning, and those kinds of approaches. And of course, they may be very also effective depending on the training and how applicable it is and so forth. So I suppose the method that I'm going to present falls under this first category. And our initial work was done by Guangyu Fang early on in 2016. And then it's based on an old observation, nothing new here again. And the old observation is the following. So this is the actual, consider that this is the line, which is the faulted branch in the system. And it's the branch which connects bus K to bus M. And then we also draw here an equivalent picture. So this is the real picture, this is the equivalent picture. Now, in the actual picture, a fault occurs along the line, somewhere along the line. And as a result of this, these voltages change from VK and VM to VK plus some delta VK and VM plus some delta VM. Now, you can show that you can remove this fault from the picture and instead put or insert two injections at both ends of the line. Of course, you have to choose these currents properly. By choosing the currents properly, you can still make these voltages change exactly the same way so that for an outsider, these two pictures will be the same. They will be equivalent, whether you are looking at a picture like this with a fault, or you are looking at a picture like this with these artificial injections. You will see the exact same picture in terms of the bus voltages. The bus voltages will be the same, post-fault voltages. And however, of course, instead of this, you'll have two injections. So this is old knowledge. Nothing new here now, but you can look at it in a different way. You can think about it this way. This is the N-bus system. These are the buses K and M. And if you write the network equations, the admittance matrix times the voltages, bus voltages before the fault. This is pre-fault voltages. And these are the pre-fault bus injections, mainly representing the generation and the load injected currents. Now, in this case, if you introduce the fault, which is done by adding this unknown injection at this unknown fault point F. So we don't know where this F is, and we don't know what this IF is, but let's assume that it's somewhere along, and I call this new bus F. So it extends my admittance matrix by one row and column. And this additional row and column will correspond to this new bus, which I call F. And since it's a very sparsely connected bus, it only connects to K and M. On this column, the last column corresponding to F, I'm going to have only two non-zeros representing these connections. And the same thing is true for this last row. And of course, on the diagonal, I'll have a non-zero term. Now, of course, my unknown, the voltage vector, will also get augmented by the voltage at this bus. And if I'm writing this equation only for the incremental solution, in other words, I'm assuming that I'm only interested in the changes in the voltage in the entire system as a result of this fault current. So I can ignore the pre-fault voltage and pre-fault injections and write this incremental equation. And in this incremental equation, I'm looking at a completely empty right-hand side current because all these injections are zero other than this unknown current IF at bus F, which is represented by this entry here. And then in the voltage solution, I'm looking at the voltage changes in every bus other than F. And then the last entry will represent the changes in the voltage at bus F. So this equation, which is the incremental equation, will look a little bit different than the previous equation, but not a whole lot. But the nice thing is the right-hand side now is completely empty other than this single unknown but non-zero entry. Now, if we go further and look at this equation, what I can do is, since I'm not necessarily interested in what's happening at point F, I can reduce this matrix by applying Cron reduction. Now, if you apply Cron reduction, the matrix, this big matrix, reduces down to back to a n by n matrix. But the nice thing is when you do this Cron reduction, you realize that you recover your original admittance matrix back. So in other words, the matrix, which was initially given here, this Y-bus matrix before the fault, will be the same matrix you will recover here when you apply the Cron reduction. Not only that, since you do the Cron reduction also on the right-hand side, this IF will get spread, will get distributed to the rest of these rows, but it will only impact two entries. Those two entries will be those corresponding to bus K and bus M. So after Cron reduction, the equation, the incremental equation will look like this, where everything is zero on the right-hand side, except for these two entries, which are corresponding to buses K and M. And this is your original Y bus. Therefore, you don't need to change anything in your admittance matrix. And these are the incremental changes in the bus voltages as a result of this fault along this line. And those are all the bus voltages that in your original N bus system. So then this solves the problem for us, because if we have actually access to measurements in the system, if I can actually measure the voltages in the system before and after the fault, then that means I can actually measure these quantities, all of these quantities. And if I can measure all these quantities, I multiply it by my known admittance matrix, and that will give me these currents. Now, can I use those currents to find, obviously, once you find the currents, you also find the faulted branch, because it will give you the non-zeros at the terminals of the faulted line. But can I also find the location of the fault? And it turns out that the answer is yes, because if you calculate these, turns out that their values are directly proportional to the distance from the terminal to the fault point. If you are measuring from this point, M, then you take IFK and divide it by the sum of them, and that will give you the percentage distance in terms of the total length of the line from point M to the point of the fault. And the opposite is true if you are looking at bus K, and the fault location measured from bus K to the fault point will be given by this. So then it's very nice. I measure these, I multiply these measured values by Y bus, I get this. I not only get the branch, but I also get these values, and from these values, I find the fault location. Well, what is missing? Why is it not so easy? Well, there are two issues. So this is basically what I just said. These are the steps. You measure delta V, you compute delta I, you're using this product, and you determine the distance to the fault. Unfortunately, there are some challenges here. before I talk about the challenges, let me show you an example to make you believe that this is indeed true. So in this example, we are looking at a 10 bus example, and it's a very convoluted picture, but it shows you that this thing works no matter what sort of crazy system you have. In this system, we have three-phase lines, and I'm sure a number of you can recognize this. This is taken from an ATP network circuit diagram. So we are using the alternative transients program to simulate this. So there are three-phase branches, there are two-phase branches, there are single-phase branches, single-phase loads, two-phase loads, and so forth. So it's a completely mixed picture of a distribution system with three-phase feeder branches, two-phase feeder branches, single-phase feeder branches, and loads. And in this case, we are looking at an example where we are applying a line to ground, phase A, B to ground fault along this line connecting bus 2 to bus 5. And the fault is applied exactly at a distance one-fourth of the line length away from bus 2. So in this case, based on our analysis here, I'm expecting, since this is one-fourth, the ratio of 1 to the third will be exactly 3. Okay, so since this is one-fourth, this will be 3/4. So if you divide this by that, you will get exactly 3. So I'm expecting a ratio of 3, and indeed that's what I'm getting. If you look at the currents for phase A, these artificial or virtual currents injected at phase A and B at bus 2, then look at the injected currents at phase A, B, and at bus 5, you see that they are roughly 1/3. This is 3 times 1500 versus 500. And this shows you an example. This is just an example, just illustrates that this approach actually works. Now, as I said, there are two challenges here, practical challenges. One is that unfortunately or fortunately, when there is a fault, we have very fast relays, and these fast relays immediately clear the fault in a few cycles. So as a result, even if you have a PMU sitting right there at the terminals, the PMU may not have an opportunity to measure the post-fault voltage, because post-fault steady state will never be reached. The relay will simply clear the fault. So this is one issue, one practical issue in terms of the measurement of the post-fault steady state voltage. The other one is that unfortunately, we don't have that many PMUs. Even though we are saying, let's measure all the delta V's so I can multiply it by the admittance matrix, unfortunately, I cannot measure all the delta V's because I don't have that many PMUs in the system. In fact, I have very few PMUs. I have maybe 10 or 15% of the buses I cover with PMUs. So how do we address this challenge? Well, the first challenge we can address by using a so-called Prony analysis. And this is another way of sort of fitting a function to a set of observations. And this is not the only way to do it, but this is fairly commonly used, especially in stability analysis. So we picked it and it works very nicely. So we use Prony analysis for that. The second challenge of the lack of measurements, then we use the sparse estimation technique to overcome that problem. So let me first look at the Prony analysis, and you can find more details in Arthur's paper here. And essentially what we are doing is we say, okay, the relays operate and disconnect the line prematurely here. So it doesn't allow us to look at the full steady state picture. If the fault is not cleared, obviously it will continue on and then we'll capture this post-fault steady state. But we can't because it is prematurely terminated. So what you can do is actually apply this so-called Prony analysis. And the Prony analysis essentially fits a curve or a function to this initial premature set of samples taken right after the fault. So it could go from here to there. And then from that point on, you use your estimated function to predict how it's going to look like. And you notice that in this case, measured and estimated quantities are on top of each other. In fact, you cannot see them. One is in blue, one is in red, but you cannot see them because they all overlap. And to show you the good match, what we did is we increased the estimation error by 100 folds and plotted it here. And you see, even when you multiply the error by 100, you see that it remains very, very small over this range. And then, of course, once you reach this point, you can easily determine the predicted steady state value for the voltages. Now, the second issue, which we talked about, that is the fact that I do not have access to all these voltages, but in fact, I only can measure a very small amount of them, gives us this picture. So instead of writing the other way, you know, Y times delta V equals IF, I'm writing it in the opposite way by taking the inverse of Y and writing this bus impedance matrix multiplied by this current vector, which is a very sparse vector. And now, since I have only access to these, I'm going to reduce my set from this nicely well determined set of equations to this undetermined set of equations, where we have very few equations, but many, many unknowns. But the nice thing is, in this unknown vector, I know that there are only two of them that I'm looking for, which are non-zero. The remaining ones are supposed to be zero. The problem, of course, is I don't know which two are the non-zero ones, so therefore I have to figure it out using the sparse estimation technique. So just to remind you, I'm going to go back here and show you what we started out with. So this sparse estimation problem, as you can see, looks identical to this picture. You have a undetermined matrix, a long, a sparse, unknown vector, and a right-hand side vector, which is also very, very small. And so it's this exact same picture. So knowing the solution to that previous generic problem, we can apply it to this. And essentially, we have to do a little bit more work because this is a complex equation and we would like to work with real numbers. So we split it into real imaginary parts, but it doesn't really change the picture a whole lot other than making this slightly less sparse, because instead of 2 entries, now you have to work with 4 entries. But other than that, the approach is the same. We apply the lasso approach, and then let's look at some examples. So this is the large 118 bus test system, which is converted, thanks to Arthur, into an equivalent 3-phase system. And so this is actually a 3-phase detailed model of the 118 bus system. And then we have only 31 buses with PMUs out of 118 buses. We assume that we have only 31 PMUs and only 3 cycles of fault transient data, because we assume that faults are cleared within 3 cycles. And then we test some examples. For instance, here we are looking at a 3-phase to ground fault at along a line connecting these 2 buses. The fault is at 20% away from one of the terminals. And these are the currents that we have solved using the state sparse estimation technique. And you notice that we have set a threshold here. We have to do it because obviously we are working with actual numbers and you're not expecting exact zeros for the remaining quantities. So we set a threshold and below that threshold, we assume that those numbers are insignificant, and the significant ones based on this threshold are listed here. And you notice that they are all referring to bus 50, phase ABC, and bus 57, phase ABC. Those are the terminal buses of the faulted transmission line. And if you look at the fault location estimation from the 50 end, it's roughly 20%, because you have to 20% away from that terminal. And then if you look at the others, terminal, it's going to be 80%, and it's roughly 80% within 1% error. And then another example here is line-to-line fault, not grounded, very close to one of the terminals, 5% distance away from one of the terminals. And again, you can see that it's determined, and it's also determining that it's a line-to-line fault, because you see there are no injections at phase C, and it's roughly 4.8, 3.9 within 1 to 2% error, and here 95 is supposed to be 95, and we get 95, 96% from the other end. Now, is it a perfect solution? No, there are obvious limitations here. And lasso is, of course, a numerical method. And you expect cases where this is not going to work entirely perfectly. And this is one example here shown when there's a fault along 101 to 102. It's a three-phase fault. We notice that the identified fault currents are all above the threshold, except for one, which is phase C of bus 102. And so, however, as you can see, since the majority of these are, out of these identified currents, almost all of them are affiliated or associated with buses 102 and 101. What we do is we decide to go into a second estimation, and you can find the details of this in, again, Arthur's paper in 2020. And this is done by applying a second ordinary least squares estimation. And what we are doing is we already know, or we already have a good guess on the branch. So what we do is we just collect the full columns from that Z-bus, bus impedance matrix corresponding to those suspect terminals, and then we solve it for these two currents. So here we are not really running a sparse estimation. We are actually running a weighted least squares estimation, because we have more equations than unknowns, because we have only two unknowns here. And if you do that, you recover nicely. And there are some examples here. This is one example, three-phase to ground faults at 5%. And you notice that we applying the sparse estimation or the lasso algorithm, we have some incorrect non-zeros appearing in the solution in addition to the correct ones. But then you go to the second OLS, ordinary least squares solution, you correct them and you get the exact solutions for these. And then another example here, again, you go through the first pass using lasso, and there is one incorrect element, and you can get rid of it by going through a second OLS solution and clear those errors. Okay, so now let me move on to a second application. And the second application is actually motivated by kinds of incidents you run into during daily operation. For instance, in the New England Control Center, it might happen that you may lose ICCP connections, ICCP links to some of the neighboring states. It could be, for instance, the New York Control Center. You may temporarily lose the ICCP link, and that will make all the connections to your New York external equivalent completely blind. So the operator will want to know if there are major changes happening in that system during this sort of blackout conditions where you have no information coming in, real-time information coming in from that part of the system, and it may last for a few minutes, 5 minutes, or it may last for an hour. So depending on how long it lasts, it may be an important issue, because you may have to be running your contingency analysis and so forth, internal system, and you may need to know what's happening in the external. So so the aim is to detect these major external area line outages, and how can we do it using PMU measurements at area boundary buses and without receiving any SCADA measurements, updates from the external system. And again, the details you can find in our PSCC paper, Miljan's paper from 2016. So I'm not going to be going over all the details, but just the solution highlight. So let's go over some of the basic approach. You can start by this DC power flow equation for the entire system. So B is your DC Jacobian, and then P is the, of course, real power injections. And this subscript 0 refers to the fact that we are looking at the base case before any outage. And you have the nice steady state angle solution theta 0, and then you do apply an outage. An outage of a single line affects, as you know, only 4 entries in this Jacobian, and I call this very, very sparse, almost empty matrix delta B. So it has only 4 entries, which are non-zero. And you add that delta B to B, and that represents your new DC Jacobian. I'm assuming that there are no load changes or injection changes. So now you'll have a new solution, theta 1, instead of theta 0 because of this change. But then you can take this product and move it to the right-hand side and call it delta P and have this equation. And in this equation, you see we have the same Jacobian, DC Jacobian remaining, a different angle, obviously, because it's now representing the post-outage state. And then, of course, the right-hand side has changed because of this artificial, this is like an artificial or virtual injection that we are creating, and that's coming because of this term here. Okay, so this we call the sparse bus injection vector, and it turns out that because of this structure, that has only 2 non-zeros, and in the DC model, they are, since we don't carry any losses, these will be the negative of each other, and then of course delta P will look something like this, the transpose of this vector. Now, you can also look at it this way. Here's the picture before the outage of the line, and then the line is physically disconnected in this picture, but then we create a virtual or equivalent representation. So instead of physically disconnecting the line, we keep the line in, so the line is still here. And what we do is we try to maintain these post-outage voltages the same by applying and adjusting these injections in red at the 2 ends. And you can find these 2 injections in such a way that these voltages will be exactly equal to those voltages in the actual outage case. And of course, in this case, this flow will not be 0 because we are creating an equivalent picture. So, in this picture, the line is connected. So the topology has not changed, but the injections are there. And the only thing is you shouldn't pay any attention to this flow because physically that flow is actually 0. And of course, you shouldn't pay attention to these injections because there are no such injections. Those are virtual injections. But this nice equivalent helps us to formulate the problem in a simple way. So this is the set of equations. This is a DC Jacobian. As I said, I'm going to skip this. And then you can partition this equation. You can partition this B by defining a set of buses as your internal buses and a set of buses as your external buses, and then collecting them and partitioning the B matrix, DC matrix like this. And by doing this, you can now consider the following. Now, looking back at the equivalent picture, as I said, before the line is taken out of service, this is the picture you are looking at. And this flow is the flow that is running through the line before the line is taken out. Now, once the line is taken out, so I call this the pre-contingency flow. Once the line is taken out, but you keep it there so that you can use these virtual injections, this flow, which is not real, but it's actually going to be flowing through this artificially kept line as a result of this equivalent picture, is actually calculatable. And you can actually calculate this in terms of this pre-contingency flow and using the elements of your DC power flow Jacobian. And for this derivation, I'm not going to be deriving it here. For this derivation, please refer to this very nice book by Bruce Wallenberg, Wood, and Chablis. There's a nice derivation of this equivalence. I'm sorry about the typo here. This is supposed to be P wiggle ST, which is representing this, not P wiggle S. So given that, now we can replace this picture by that picture and assume that these are the two injections at the two ends of the outage line. These are the two terminals S and T buses of the outage line. And then now let's continue with the derivation. I'm going to come back to this. Once you write it in this form, the partition form, you can take this and you can eliminate from this equation delta theta E. And if you eliminate it, you get this compact picture. So in this compact picture, all we did is, as you can see, we have eliminated delta theta E from the equations. And we wrote everything in terms of delta theta I, which is this. So I'm writing everything in terms of delta PI, delta theta I, and delta PE, and I'm eliminating delta theta E. And obviously, you can do it easily by applying Cron reduction on this coefficient matrix. So that's what we are doing, actually. So this is the Cron reduction. And when you apply the reduction on that, you get a matrix which I now call M, which is nothing but this product. And the equation looks something like this. So if you call this whole thing, which is actually a vector, J, and you see this vector is actually a known vector because it includes the changes in the injections in the internal system, which you have because you can run your own estimator, state estimator for the internal system and develop these vectors, delta PI. You also have either measured or state estimated values of this delta theta I. So both of these are either measured or estimated because they are in your internal system. So this J is a known vector. M is actually this, which is directly coming from the DC Jacobian. And therefore, in this equation, the only unknown is delta PE. Now, looking at this equation, I'm going to take you back to this picture. You see that this picture is identical to that picture. This is a right-hand side, which corresponds to this. And you may not immediately see that this is a short vector because it's a short vector because actually this BIE, this partitioned small matrix, has a lot of zero rows because the only non-zero rows will correspond to the buses which directly connect internal and external systems. The other buses, strictly internal buses with no connections to outside, will have zero rows. So as a result, even though this appears like a big matrix, actually the usable rows out of this are very, very few, and they actually represent the boundary buses between the internal and external system. So this is a very short vector representing this vector in the picture. And this long unknown vector is actually this delta PE. And remember the picture of delta PE. You see it's a very, very sparse vector with two unknowns, but the problem is I don't know where these unknowns are because I don't know the terminals of this line because I don't know where that line is. So therefore, you know, this picture is very much like that picture, and we can use this, again, sparse estimation problem solvers to solve this problem for delta PE. And this is precisely what we do. We apply the lasso algorithm to this, and I'm going to skip this from here, but you can certainly remember this general formulation. So that's exactly what we are using here to solve this lasso problem. So example, if you take a look at this very simple 14-bus system, consider this to be your internal system, this to be your external system, and these lines, any one of these lines can be outaged, and you are supposed to rely on your measurements at these two boundary nodes, bus 5 and bus 4, to determine which line is actually taken out of service. And here are some results. You notice that some of these results are direct. You know, we are showing that, for instance, when this line is taken out, we were able to determine that that was it, and this was the flow. So I was supposed to get this flow, but I got that flow, and this one, instead of this, I got that. So these are close enough values for us. But then there are also these cases where you can see that the lasso algorithm during the first pass determined that another line, or estimates that another line is taken out. Now, these cases, when we saw these cases, we were a bit disappointed. But then we figured that, remember, going back to this derivation, even though we don't know which line is out, once we determine the outage line, we know that we know the post-contingency flow approximately, because this is a DC approximation. So if we know the pre-contingency flow, we can guess the post-contingency flow based on this formula. So therefore, once you get this result, if these two don't match, because for 9 to 10, the expected flow is this much, but you see we only got that much coming out of lasso. We say, well, there's something wrong here. So what we do is artificially we set this column to 0 corresponding to this specific branch. So we sort of ignore this branch and rerun lasso. And then in the second cycle, we actually get the correct outage line and sort of the equivalent value, which is expected. We're expecting 24 and we got 23. And the same thing happened here. And in fact, sometimes it takes more than one cycle, 2 cycles before you get to the actual outage line. But in all cases, as you can see, we were able to find the correct outage line by going through this logic. And then we applied it to also the big system, 118 bus system, where these are the internal buses defined as the internal buses. These are the external. And then we looked at several cases. And in this case, we noticed that we can improve on detection accuracy by adding few PMUs in the external system. So of course, initially, we assume that there are no PMUs in the external system. We are strictly relying on our boundary measurements and the internal state estimation results. But we can certainly improve if we somehow have access to 1 or 2 PMUs from the external system. And this is shown here. In the case where there are no PMUs assumed in the external system, we were able to identify 79 out of 98 outages in the external system. Those 19 undetected outages happened to be electrically far away from the internal system boundary. So these were some of the very remote branches from the boundary. And they may not be that important for the internal contingency analysis. And then by adding a few more PMUs, you see we were able to reduce this 19 down to 5. And by adding 3, they were reduced down to 3. So it's possible to improve on this further if you populate your external system with a few more PMUs. Okay, now I come to the last topic, which is the use of PMUs in tracking the transmission line parameters. This is the work by Peng Shang, and his paper is listed here. And the idea here is transmission line parameters are important because they are used in applications like relaying, but they also change. And if you don't have the exact line parameters, you may be unnecessarily biasing some of the other applications which use them in their databases. And the problem is not necessarily in one parameter, but in the whole three-phase model, because now you're talking about coupled three-phase lines with an impedance, series impedance, and shunt admittances. And the question is, what if we have access to full PMU measurements at both ends of the line? You have full voltage and current measurements from sending end, full current measurements and voltage measurements from the receiving end. Can you actually track these parameters of the three-phase model and track the changes and correct errors? And to find out, we sort of formulated it, looked at the number of parameters that we are supposed to be tracking, and we noticed that there are quite a few. If you look at the series impedance matrix, since it's always symmetric, you'll have 6 entries, and these are complex. Or if you, in terms of real, 6 times 2, you have 12 unknowns, real unknowns. And here, assuming that you have conductances are 0, you have strictly capacitive connections, you will have 6 unknowns here. So adding them 6 times 2, because these are complex, we have 12 plus 6, 18 real unknowns. Now, what about the measurements? Well, the measurements are, in terms of real measurements, there are 12 if you are looking at currents, because if you are looking at 6 currents, 3 on each end, 3-phase measurements on each end, and then of course they are complex, so you multiply by 2 in the rectangular coordinates, for instance, you get 12 measurements. And when you write the equations, you can either write them to estimate the voltages like this. So you relate the currents to the voltages, 12 currents to 12 voltages through a matrix. And also you can write the same equations, the same measurements in terms of the parameters. So in that case, that would be the current measurements written in terms of the parameters, those 18 unknown parameters, and a coefficient matrix H sub V. So we are looking at 2 different equations. One equation is where the currents are related to the voltages through this H sub P meaning this is a matrix which entries of which are functions of the system parameters or line parameters. And here we write the same equation, same measurements in terms of the unknown parameters, where the coefficient matrix is a matrix where the entries are functions of the voltages. So either way, when you look at it, you have more unknowns, 18 unknowns, than measurements. We have only 12 measurements, but 18 unknowns to solve. So, and then obviously, I mean, H sub V is a underdetermined matrix. It's 12 by 18. You know, you have less rows than columns. So when we run into these problems, typically, especially this kind of problem, we always say, okay, well, P is not a changing parameter from one scan to the next. So since these are constants, let's use multiple scans. You know, instead of using a single scan, we can use 3, 4, 5, 10, 100 scans of I, where the I will increase and increase the redundancy, but P will remain constant. So that way we can increase redundancy and finally do a least squares type estimation. Unfortunately, this is not quite possible in this case because when you put this H sub V together for multi-scan case, you notice that it's extremely ill-conditioned. In fact, we are showing it here for a case of 100 snapshots, and this represents the singular values. And the ratio of the largest to smallest singular value is typically a good indicator of the conditioning, because it's the condition number actually of the matrix. The larger it is, the worse ill-conditioned the matrix will be. So in this case, as you can see, it's very, very significant, 10 to the 4, meaning that it's the solution of such an estimation problem will be very, very unreliable, numerically very unrobust. And then you might say, okay, why don't you wait for the voltages to change? Why are you taking so close snapshots? Well, the problem is if you wait too long, then you are running the risk that the parameters may change during that time. So you are no longer looking at a constant parameter estimation. So given that, we had to do something different. So what we did is we put together actually a dynamic estimator for the parameters with this simple discrete time model, which is actually, as you can see, is a random walk model. And then the discrete time measurements, which are the current measurements, written like this. They are underdetermined, obviously, but we are talking about the Kalman filter application here. So observability may not be an issue here if we are doing it with enough scans, enough samples. Now, the problem, of course, is we also don't know the voltages. So when you write this equation, we pretend that we can actually build this matrix H. But to build this matrix H, you need the voltages, but we don't know the voltages. I mean, we are measuring them, but of course, these measurements may be wrong. So we cannot really rely on the measurements, assume that they are perfect. So what do? Well, we better estimate those voltages, and we can certainly estimate them using this kind of, linear state estimator for those 12 voltage values, unknowns. We can solve the estimation problem using weighted least squares method. And then in this case, of course, we will be using a model where in the model, this coefficient matrix is a function of these unknown parameters. So we run into this very strange situation where there's a voltage parameter interdependency. So voltages are estimated using parameters and current measurements, but then the parameters are estimated using voltages and the current measurements. So what we are estimating here are used as if we know them in this part, and then what we are estimating here are used as if we know them in the first part. So, so that means we need to do an iterative solution. So that's what we did. So at each scan, what do? We iterate between state and parameter estimation. The voltage estimation relies on the most recent parameter estimates and, of course, the measurement of currents. And the parameter tracking is done relying on the most recent voltage estimates and then, of course, doing the suppressing the current measurement noise using the estimator. So, and then, of course, we terminate the iterations when the two successive parameter estimates are very close, or we reach some sort of upper limit on the iteration count. Okay, so this is the approach. You do the estimation on the voltages, and then you go back to the parameter tracking, and then you check the termination criteria, which is basically the changes in the parameters. And if it's not satisfied, you go back and repeat it. And then you go back, once you are done, you go back and you continue with the next scan. So this is a dynamic estimator going from one scan to the next, and some results here. In this case, we are looking at these 18 parameters that we talked about for the line. And this is the case of the constant parameters. So the parameters are not changing over time. And you can see these are nicely followed for each case. And then we applied some slowly changing scenarios where these parameters are slowly changed over time. And you see the way the dynamic estimator is following these dynamically changing, slowly varying parameters. And then we also looked at abrupt changes, sudden changes in those parameters, those scenarios. And then we have also validated the estimator for those scenarios. And then we also collected some actual recorded snapshots coming from the New England ISO measurements along a feeder. And then we tried to monitor the parameters. And of course, in this case, parameters are not changing. These are actual system parameters. And they have given us the values from their database. And these are the values they have given us. And then when we use the data, the measurements, and estimated them, we noticed that our estimated mean value over a period like this matched sort of closely those parameters. At least they are not very far off. So this was more of an experimental validation. And this is strictly positive sequence, by the way, this particular one. And then lastly, before I stop, I'd like to mention this. You might say, okay, we don't have that many PMUs. We cannot monitor each and every line by a couple of PMUs at each end. What can we do in that case? Can we actually track the parameters of all the line parameters without having one PMU at each bus? And for that, you need to have another sort of setup where you use the existing PMUs to do a full state estimation, linear estimation for the system, and then use those estimated values as if those are PMU measurements in your dynamic parameter estimation. So these are, of course, they require additional work. For one thing, you need to make sure that the PMUs you install are properly installed so that the system is observable. And not only that, the branch parameters are observable and so forth. So then I'm going to skip this and we'll show you the solution for this only for the positive sequence because the three-phase is a lot more engaged in this case. So for the positive sequence case, let's consider the picture like this. And this is very much like the previous case, except I'm only doing it, producing these equations for the positive sequence instead of just a three-phase full picture. And we have the measurements, the current measurements, again, written in the same form, in terms of the parameters. And we again form the, dynamic equations, discrete time equations for the parameter dynamics, which is again, random walk. And then we apply a Kalman filter to track these. And to do that, first of all, the measured voltages obviously cannot be directly used because they may contain errors. So we need to have a system-wide state estimator to do the state estimation for the bus voltages. And then once we do that, we also need to have the fact that we have limited number of PMUs. Not all voltages can be measured, so we need best locations for these PMUs to place. So we need a way of locating these best locations. So we developed, okay, so this is the linear estimator. These are the measurements. This is the state estimation equation for the whole system. So this is well-known, PMU measurement-based linear state estimator. The only extra stuff here we have is the zero injections. We added them for added redundancy since they are free measurements. And then we looked at how to do PMU placement, not only for observability, but also to be able to track the parameter errors or the parameters of the lines. And it turns out to be, again, a linear programming problem, as you can see here. And I'm going to skip the details because they are all in Pang Shan's paper. And for instance, in the case of the 14 bus, these are the locations we determined for the PMUs. As you can see, they are significantly larger in number than the ones you would put if you were just doing it for observability of the states. And then some numbers here. As you grow the size of the system and you look at the required number of PMUs, in the case of observability, like if you are just running a linear state estimator, these are the number of PMUs you need for these systems. And if you are doing state estimation as well as tracking parameters, then you need significantly more number of PMUs. As you can see, there are roughly twice as many as you would require in case of just observability of states. Okay, so and just these numbers, some simulation results, again, for the constant parameter case for G and B and the shunt susceptance, starting from a random initialized value, it converges. It takes a while to converge, but after a few scans, it converges nicely. And then these are the cases where the parameters are allowed to vary smoothly and parameters are tracked. And then these are the cases of abrupt changes in the parameters. Again, the dynamic estimator follows these as expected. Okay, so with that, I'm going to stop. Just to wrap up very, very quickly. These sparse estimation methods are very, very commonly used by many, many applications, not only in power systems, but in many areas. So it's good to exploit them if possible. And we showed a couple of examples here. One is on fault location, the other for the external system line outages. The complete set of parameters for a non-transposed transmission line can be dynamically tracked using PMUs if you have PMUs at each line terminal. If you don't have such luxury, having PMUs at each line terminal, then you can go for a system-wide state estimator using limited number of PMUs and then combine it with a dynamic parameter estimator for all the lines, and that might be a nice solution. And also, finally, one last comment I have is that typically we pay a lot of attention to state estimation, estimating the states, removing the bad data and so forth in the measurements. But we pay less attention to the network model and parameter errors, even though they are a big source of bias in estimation and the subsequent applications that use results of estimators. So I think we probably should be, they probably should receive equal attention for all the network applications. So with that, I'm going to stop and take questions.